Hello all, welcome to VLSI friends. Today I am going to explain modular testbench architecture with example of half adder. What you will learn today. First, what is testbench? After I will explain why we use architectural testbench instead of directly writing simple testbench. And then you will see overview of testbench architecture with block diagram. After I will explain the each block of testbench architecture using the half adder example. And lastly, I will run the simulation and observing the output. What is test bench? A test bench is like a virtual lab setup used in simulation to test your design. It is not a part of actual design. It is written separately just for testing. The test bench is used to generate the input and send them to the DUT and observing the output. It is helps us to verify whether design is working correctly or wrongly before implementing in real hardware. The entire experience runs in simulator, so no physical hardware is needed during testing. Assume this is the DUT. DUT means design under test. This is our actual design. After we will write the test bench separately. Uh, we are connect this test bench and DUT using interface. By connecting using interface, we will verify the our DUT using test bench. Why we use architectural test bench instead of direct test bench? In direct expense, we write everything in one block. This is the example of our direct expense. Here I write everything in one block or one module. Here this is the example of the half-adder test bench. And here output is declared as a res data type and input declared as a where data type. Here A and B is output to the half-adder test bench and input to the DUT. And someone carries output to the DUT and input to the half-adder test bench. After declaring input and output, I instantiate the module and inside the initial and begin inside the initial block, I write all the values directly. But in architectural test bench, we generate the input randomly. This is okay for small design, but it becomes messy and unmanageable in large projects. We can't easily reuse or modify code when everything is written in one place or one block. That's why we follow modular architecture in TestBench. Here we use different classes to develop the TestBench. For example, generator class. It creates the input values for testing. Next driver. It sends the input to DUT. Next monitor. It collects the output from DUT. Scoreboard. It checks the output is correct or wrong. Here each block has its own role, so test bench become organized, reusable, and scalable. In this slide, we will see test bench architecture with block diagram. This is the DUT. DUT contain our design. We want to write test bench to verify our DUT. Here we first implement the transaction class. This transaction class contain all the input and output inside that class, and it is act as a data packet that is shared between different components of TestBench. Here we first give this transaction to generator. Generator is a class that creates the random input values for DUT using randomize method. After generating random input, we store it in transaction class and we send this transaction class to driver using the mailbox. This all I will explain in code in further slides. The driver is also a class. It gets the transaction from generator using the mailbox and extract the data from transaction and send it to DUT. Here, driver is not directly send the data to DUT because there is no direct connection between Testbench and DUT. We send the data from driver to DUT using interface. This interface. Here, driver and interface is not possible to communicate with each other directly because driver is a class. Class is operate at runtime, but interface is defined at compiler time, so they cannot directly access each other. Next, monitor. Monitor is also a class. It reads the output from the DUT using virtual interface and here it creates the transaction object and fill it with our observed output values and uh, and send it transaction class to scoreboard using the mailbox. We sent the our transaction class to scoreboard using the mailbox. Scoreboard. Scoreboard is also a class. It receives the output values from the monitor using mailbox. It also calculates the expected output using the input values and it compares the expected output values versus actual output values come from DUT. And if both values are equal, it return as a your verification is success. If it is not equal, it return as a the verification is failed. Next, we will design the environment class. From this environment class, uh, we bring all we bring together all test bench component in one place, and it contains the handle of the generator, driver, monitor, and scoreboard. And in detail of environment class, I will discuss in further slides. Next, I create the test file, and the test file is used to create the object for environment class. Testbench top is a high-level module. It connects the testbench with DUT, and here we also instantiate the interface. This is the overview of testbench architecture, but sometimes we use two monitors also. That I will explain in next slide. This is the over. This is the overview of testbench architecture with block diagram with monitor. And here this is the packet, means transaction class. It contains all input and output values. And we give it to generator. Generator is a class used to generate the input random values, and it give that values to driver using the mailbox. Driver receives the values from generator and give it to the DUT using interface. This is the DUT used to produce the output. Here we use two monitors, monitor 1 and monitor 2. These two monitors are used to read the both input and output values from the DUT. Monitor 2 will directly give that values to a scoreboard, but monitor 1 give that values to the reference model. Reference model is a model same as a DUT. Both reference model and DUTs are working in same way, but DUTs came from design team and reference model was built by verification team to generate the expected output. The reference model will generate the expected output and give it to the scoreboard using the mailbox. Here, scoreboard compares the both outputs. One came from reference model and another one came from monitor 2. If both outputs are equal, scoreboard returns your verification is successful. If it is not equal, it returns your verification is failed. From this slide, I will explain Each block of test bench architecture. In this slide, I will explain our design of adder. This is the block diagram of half adder. It takes two input values A and B and produces the two output values sum and carry. This is the truth table of our half adder. We solve this truth table, we get sum equal to A XOR B and carry equal to A and B. This half adder takes two input and inputs A and B and produces the two outputs sum and carry. Sum is equal to A XOR B and carry is equal to A and B. In this slide, I will explain the transaction. Transaction is a set of inputs and output values. Basically, a transaction is a class used to store one set of input and output values. It acts as a data packet that is shared between different components of Testbench. The input values A and B are declared with rand keyword to allow generation of random values. The output variables sum and carry are declared as normal variable, no need to randomize them. And this transaction object is used to transfer data between generator, driver, monitor, and scoreboard. And I will show the code for design and transaction in my VS Code. This is where this is Verilog. This is Verilog code for our design of adder. Here we first declare the module with name of adder, and we declare four ports A, B, S, and C. Here we declare the direction of our port, input A, B, and output S and C. S is sum and C is carry. This is our actual logic of our design. Here S equal to A XOR B and C equal to A and B. And we end this design uh, by closing the module. Next, we will see the transaction class. We, these two lines are used to we can call our transaction class in anywhere in multiple times. This, this is our actual transaction class. Here A and B we declared as a rand because these two are input. We generate these two random values, and S and C are outputs. We declare it as a normal variable using the logic data type. Here we declaring the function with name display. This function is used to declare the current status of our input and output values. Next, we will see the generator class. In this slide, I will explain the generator class. The generator is a class that creates the random input values for DUT. It generates the different input combination using dot randomization method. It creates the handler for transaction class to store the input values. It uses the mailbox to send the generated transaction to a driver. Here we can control how many transactions to generate using a loop. Next, we will see the code for generator in VS Code. This is our generator class. Here we first include the transaction.sp file, which defines our transaction class. In generator class, we do main two things. First, we will create the handler for transaction, and next we will create the new mailbox. Inside the new function, we connect the local mailbox to one password from outside using this statement. This mailbox is password from environment file or environment class. Here we come to main task. First we create the instance for transaction class and Using trans.randomize, we create a generate the random input values. After we print the generated values and present output values. And using this statement, we will put transaction class to mailbox and transfer to driver. This is the code for our generator class. Next, I will explain the driver class. Driver sends the input to DUT. The driver is a class that receives the transaction from generator and sends the input signal to DUT through interface. It uses a mailbox to get transaction from generator. It extracts the input values A and B from the transaction and drives them to DUT. The driver is not directly connected to DUT. Instead, it sends the input using the interface. However, classes operate at runtime while interfaces are defined at compile time, so they cannot directly access each other. To solve this, we use a virtual interface. It acts as a bridge that allows class-based components like driver to access the interface signal during simulation. In this slide, I will explain the virtual interface. A virtual interface allows the class to access signals in the physical interface. We pass this inter we pass this virtual interface handler from the top module to class. It is used in driver and monitor to interact with DUT through the interface. Without virtual interface, class-based components cannot directly access the signals from interface. Now I will explain the code of our driver class in VS Code. The driver class is responsible for sending the input to DUT. Here we first include the transaction.sp file just like before. Inside the class, we declared two things. First, we declare the virtual class. Here we declare the virtual interface, and here we declare the mailbox Gen2 drive. Inside this new function, we connect to our virtual interface. One interface is our class interface. Another virtual interface is given from environment. Here we pass the this virtual interface from environment, and we also connect this to mailbox. Now we come to the main task. Here we first create the handle for our transaction class. From the statement, I will get the transaction class from the generator. In this stored statement, I will assign the transaction value to our virtual interface. These two statements are optional. Using this display function, I will display the current status of our input values A and B and output values S and C. Next, I will explain interface in my presentation. Interface. Interface connects the DUT and Testbench. The interface is used to group DUT signals in one place. It contains all input and output signals A, B, S, and C. This makes it easier to share signals between classes like driver and monitor. And this helps to reduce the port level connections in top level module. And let's see code in VS Code. Here we use keyword interface to declare the interface, and uh, and here we declare the all our signals A, B, S, and C. This is the interface. Now I will explain the monitor in my presentation. Monitor, it observes the output values from DUT. The monitor is a class that reads the output from the DUT signal using the virtual interface. It creates the transaction object and fills it with observed output values. And it uses a mailbox to send this transaction to Scoreboard. Let's see the code for monitor. This is our monitor file. Here we first include the transaction.sp file, and in monitor class we first declare the virtual interface, and after we will create the one mailbox called mount to score. Inside the new function, we connect the virtual interfaces and mailboxes, and this is the in virtual interface declared in this class, and this is the virtual interface passed by uh, yeah, passed in the environment class, and this is the mount to score mailbox created in this class, and this is the mount to score mailbox which is passed by environment. I will explain in further slides. Now we come to the main task. Here we first initiate the handle for the transaction, and here we create the object for transaction class. Here we assign the virtual interface values A and B generated by the DUT to the trans.A and trans.B. These are our transaction class variables. Here we assign the sum and carry produced by the DUT. We assign to the our transaction object S and C. Here we put the transaction class to the mount to score mailbox to transfer it to scoreboard. And using this display function, we display the current status of our input values A and B and output values S and C. Next, I will explain the scoreboard using my presentation. This is the scoreboard slide. This scoreboard is used the output values from the monitor. It calculates the expected output using the input values. It compares the expected output versus actual values from DUT. If there is any mismatch is found, it report as a failure. Otherwise, it will return the success. Let's see code in my VS Code. This is our scoreboard file. First, we include the transaction.sp file as like before to access the transaction class. In our scoreboard class, first we initiate the mailbox mount to score. Inside this new function, we will assign this to mailbox. One is declared by our class. One is declared by our scoreboard class, and another one is passed by environment class. Now we come to the main task. Here we first yeah, here we first create the handle for transaction class. After we get the transaction class from the monitor, this is the code block. Here we do main two things. One is generating the reference model, and another one is comparing the expected output and actual output produced by the DUT. And this function is used to display the current status of our input and output values. This is our actual reference model. Here we calculating the XOR of A and B manually, and here we calculating the AND gate of A and B manually. If XOR of A and B is equal to trans.s, which is developed by our DUT, and if the AND of A and B is equal to trans.c, which is developed by DUT, then our scoreboard is returns the result is expected. Else, else scoreboard will return result is not expected. This is the code for our scoreboard. Next, I will explain the code for. Next, I will explain the environment in my presentation slide. Environment. The environment is a class that brings together all testbench components in one place. It contains handle for the generator, driver, monitor, and scoreboard. It contains the mailbox to allow the communication between these components. The environment acts as the central unit that starts and manages the testbench operation. A virtual interface handle is declared in environment and passed to the driver and monitor. Let's see the code in VS Code. Here we first include our all files generator.sp, drivers.sp, monitor.sp, and scoreboard.sp. Now we come to the class environment. Here we first create the handle for each class. Here we create the handle for each classes, generator, driver, monitor, and scoreboard. And here we create the mailbox M1 and M2. Here we create the virtual interface. Inside the new function, we create the object for these all components. Here we create the object for our mailbox. Here we create the object for our components like generator, driver, monitor, and scoreboard. We pass M1 mailbox to the generator and virtual interface and M1 mailbox to driver and virtual interface and M2 mailbox to monitor and M2 mailbox to scoreboard. If we come to the test task, here it uses the fork join block to run all components in parallel. Inside this block, we will call all main tasks of each component. After completing this, task run will call test. Uh, by executing this test, we will finish our simulation. This is our the environment class. Next, I will explain the test class. In this slide, I will explain the test. The test is a program block that starts the simulation process. It creates an object of environment class. It receives the real interface from the top module and passes it to the environment. Let's see the code of test. Uh, let's see the code of test. This is our the code for test.sp file. In this code block, here we just create the handle for the environment, and here we give the and here creates the object for environment with passing interface. And after I will call the dot run task to finish the simulation. Next, I will explain the top module. Testbench top. The testbench top is the highest level module that connects everything together. It creates the real interface instance and give it to test. It instantiates the DUT and connects it to interface signal. This is the entry point for simulation where everything begins. Let's see the code for testbench stop. This is the code for our testbench stop. Here we first includes the interface.sp and test.sp file, and here we create the handle for our interface and pass it to the test, and finally here we instantiate our design module. I will show the simulation in Questa Sim. The CD is the CD is referenced in the directory. Here we I here we I write all the code in this folder. To first we compile this all. Here we first compile this all files using the vlog keyword, vlog comment. Here we compile here we compile all our files. Ignore this warning. This is not affect to our output. We are simulate our top dispense top module. Use the vsim comment. Sorry. We just give our module name, not file name. Use vsim comment to simulate our use vsim comment to simulate our module. The simulation is completed, but we see our output. We want to run this. Here you see the in generator class it generates the input a equal to 1 and b equal to 0. This is the driver class. This is driver class input and output values. This is the monitor class input and output values. Here scoreboard was compared the expected output value and actual output value. Here both expected and actual output values are equal. That's why scoreboard was written the result is expected. And this is our output. Now we if you want this code, I was given link in description. You can download from link. And and if you want to give any feedback to my class, you can give it through this link. It was given in my description box also. It will help me to improve my presentation skill. Now I ending this presentation. Thank you.